Oh, no. And he was like that one. No, where? Is it like a thing for like people who were going to Wisconsin? Yeah.
That's so cool. How was that happening?
He was like sitting at the table and he's like, oh yeah, I'm the best. I'm like, oh, like Alex, like, oh, do you know? Yeah. You were the first guy asked.
That's because he's like
overall, it was you, and then he could like right
with their application program.
so that's like a little schoolgirl like crush or something.
See you.
You're right. Ballet. What was that? Come on.
See you.
You're not a teacher.
You gotta do this one.
I didn't know.
So you might respond. Is that
everything was like,
No, I can really like.
Oh, awesome.
With him, he's between like. They got way older. I could see the best friend from
No, I gotta need response. No, I am.
Santa Cruz or they had a
Well, if I stay in the States.
that's right.
right.
If they're going to go to say Saturday at 5 at night.
Don't say anything. No, it's
Switzerland. Like they were all sold out.
Netherlands. No, yeah. Amsterdam, right.
Yeah, I had an interview this morning. You're driving straight to Ireland, and it was really hard.
Why?
From there we
Because
went to
they accept 225 students
and then we got there like
of 900, so I got cut down from like 900 students to like 400, so I got, I think it was 400 to something. Now I have to get cut down to 50%. So I had an interview at 6 in the morning.
we had was so tired like the entire day. And then
Who's not here last time? Oh, you didn't get the handout. Did I give you the man's
So yeah, and then
No.
Oh, okay. I wasn't here for
the
that.
other interview,
You got it.
Yeah.
like I was there for 2 hours and I never showed up.
Yeah.
On Skype.
Like trying to get.
I was there, my interview was 6.
They never showed up?
Yes, they never called me over Skype, but they sent me like a friend request to be like 100% like.
That was easy. Get the fucking chase it.
And then they blamed it on me.
Here,
Yeah.
Thank you. That's
All right.
Lots of people and stuff, so they did.
I just like trying to prepare.
All right, today's really been a crazy day. It's about to get crazy.
Wait, is the last
The reason why it gets a little crazy here is because of course what happens on Wednesday of this week? Oh, it's our Magic Mountain field trip. Where are you supposed to meet and when?
Don't know.
Oh, exactly. At 9:15. Remember, go to your period 2 classes until 9:10. And you are dismissed. We meet down at the flagpole at 9:15. I take attendance. Then we get on the buses. However, there's about 180 kids that are going to be getting on the 4 buses. So I have to distribute all of the kids evenly. So what I'm going to do is I'm going to give you a little piece of paper. If you get yellow, you go on the yellow bus. If you get pink, you go on the pink bus. If you get purple, you go on the purple bus.
Oh, the bus is
Think of
actually
this
colored
as like
purple.
your means of getting on the bus. Not only will we leave school, but also when we leave the park and come back to school on the other end of the day. So this is your color. You're on the yellow bus. You're on the pink bus. You're on the yellow bus. You need to have one of these in order to get onto a bus. You need to have one of these in order to get onto a bus.
Okay, so is my bus actually going to be pink?
No, it's not going to actually be pink.
I'll give you 10 purples, 3 for and 2 yellows.
There you go.
Oh no, Nash is purple. What are you? I'm pink.
Yellow.
Oh my god, hey. Yellow?
All right, Henry, you get pink.
Hot pink. Who else has? I'm not gonna do anything until I know what other people have.
All right, so make sure you bring this with you on Wednesday morning because you need one in order to be able to get on a bus. And then, of course, come back.
I just cut out my own.
All right, let's go ahead and get started today. Everyone, please take out your notes.
Somewhere over the rainbow.
we have
Go ahead and get started, please. Everyone take out your notes.
that I know.
Recall where we were at the end of class last
Once in a little
time.
while.
Lena, Henry. Recall where we were at the end of class last time. We were starting to talk about stringed instruments. Okay, and when you pluck a guitar string, remember that it creates the n equals 1 standing wave. Pluck a string, such as guitar string, etc., creates the n equals 1 standing wave, which remember has one antinode here in the space L. If you recall, it looks like this. And then the frequency of the note that is being played is then therefore the fundamental frequency of the string itself. The fundamental frequency is the V over 2L quantity. Once again, the V here initially is a little bit confusing. The V is the speed of the wave on the string. The speed of the wave on the string is equal to the square root of the tension divided by the linear mass density. So if I rewrite the expression here for the fundamental frequency in terms of this speed V being these quantities, this expression right here explicitly now shows why stringed instruments are so versatile. The reason why they are is because you can control all these different variables. You can control the length L by pressing the string down to the fretboard, change the tension in the string, or just, of course, simply change the string itself. If you move from one string to the other, you're moving from one value of mu to the other. So this little expression here all by itself explains why stringed instruments are so versatile. Okay, let's take a look at a couple of simple problems associated with the use of this expression here. It's actually really easy to manipulate. These problems are pretty straightforward. We'll specifically take a look at this. Okay, so let's begin by just playing a different note on a single string by placing your finger appropriately down in some position on the fretboard. Say it like so. Everybody enjoy the lockdown drill?
It was really fun. We made a barricade at the door.
Yes, we did in my room too.
How do they put these out? Psychological distress. Walk out. Like you get Brazil freaking out.
Okay, now those of you that do play musical instruments may recognize the two notes that are being played here, 440 hertz and then 528 hertz. Okay, we're changing the note that is being played here in the problem by just manipulating the length L. Now here's typically how we go about these types of examples. You'll kind of see me do the same thing for the remainder of the examples today as well. What we'll do is write two equations, one for each frequency. So we have frequency F1, we'll call it as 440 hertz. The length of string, we'll call it L1, associated with that is 50 centimeters. We do have to work in metric SI units, so the length L is 0.5 meters. Okay, now the equation that describes this frequency, we'll just write in the following way. We'll have F1 as 1 over 2 times that length L1, and then multiplied by our square root term. And then in just a moment, I'm going to rewrite the same equation for F2, but when I do, the only thing that's going to change is not the tension, not the string itself, so not the density, but the length. So then therefore, I'm going to have an L2 simply in that expression, if we now have this frequency F2 of 528 hertz. So the unknown here is going to be the length of this string. That is where we have to place our finger on the string, pressing it to the fretboard, but none of the other quantities will change. Yes,
Is T here tension or?
yes, T is tension. So it's important to realize that the V in all of this is the speed of the wave on the string. Okay, now the equation F2 then we'll write in the following way. 1 over 2 times L2, but then multiplied by the same square root, where all the terms there are exactly the same as they were before. So the only thing that's changing here, the only parameter, if you will, that's changing from one frequency to the other is the length. So we basically end up here with just two equations and two unknowns. The two unknowns are L2, which is what we're looking for, and the square root term, which we really don't care about in this example. The easiest way to approach the algebra in this problem, and in problems that are similar to this, is actually to just take one equation and divide it by the other. Watch what happens when I do that. So I'm going to take F1 divided by F2. It really doesn't matter how I do this. I'm going to have, first of all, the expression for F1, which was the following. And then now divide by the expression for F2, which is this guy here. And notice that if you approach the algebra in this way, then immediately a bunch of stuff starts to cancel out. The square root term cancels out completely, like so, as does the 2 here and here. And then if you just kind of clean up what's left, you got to be a little bit careful here when we do. We're going to have, first of all, 1 over L1 in the numerator, but then divided by 1 over L2 in the denominator. If you simplify a little bit, this ends up being L2 over L1, like so. And then what we have to do here, with what's left, is cross multiply a little bit and solve for L2. So move the L1 simply to the other side of the expression. This then gives us L2 as being equal to the following. So a ratio of frequencies here multiplied by the initial length. Now my ratio of frequencies here is a number that's less than 1. We have 440 divided by 528. This means that the length of string L2 is going to be less than L1. That is, if you shorten the length of string, you're going to end up with a higher frequency sound as we do in this example. Okay, so now numerically, very easy. We have 440 over 528, and then multiply that by 0.5 meters. And this comes out to be about 0.42 centimeters, or 0.42 meters, excuse me, 42 centimeters, like so. Now, just to be exactly clear on what the L's are in a problem involving the guitar, so if I just pluck the string by itself, let's say that's 50 centimeters, that's just like this, like so. And then if I place my finger here on the fretboard, such that now from here to here is the 42 centimeters, and then when I pluck the string, we hear the higher pitched sound like so. But what I do, by placing the string all the way down to the fretboard, it's like I kind of lock this portion of the string here in place. It actually doesn't vibrate at all. If I want to, I could play this section of the string as well. I could do something like that. But the L in the problem is specifically from my finger here to here. That's then the 42 centimeters that we found here in this example. How many of you play a stringed instrument? Guitar, violin, so on? Okay, a bunch of you do. How often per session do you have to tune the instrument usually? Once at the beginning. Maybe if you play for a long period of time, you may have to tune it a little bit again later on. The reason for that is because only very minute changes in tension with the pegs leads very quickly to the instrument then getting out of tune and then changes the frequency. You also particularly have to retune the instrument if there are wide temperature changes, like if it's really hot or if it gets really cold. And the reason for that is because the temperature changing will lead to the instrument actually expanding if it heats up, and then contracting if it cools down. That will then cause the pegs to twist a little bit, thereby changing the tension. But it's only small changes in tension that are necessary to change the frequency. Let's take a look at what happens when you tune an instrument, such as with the violin.
Mr. Shaw, how was your weekend?
It's all right.
Yeah. Did you have your Coachella yet?
Hmm?
Did you have your medal Coachella yet?
No, it's not until May.
Oh, what's that called?
Maryland Dead Fest.
Yeah, yes.
It's like 25,000 metalheads descend on Baltimore. in May. Okay, now what we're going to do in this example, like in the last example, is write an equation for these two different frequencies and then relate them to each other. A lot of these problems all kind of go the same way, as you'll see. All right, so here's how we'll think of this problem, much the same as the previous example. we're going to have a frequency F1 here of 435 hertz when the instrument is slightly out of tune. And now the equation associated with that, I'm going to write in terms of a tension T1. Like so, because now the only variable that's going to change when we go from one frequency to the other is the tension in the string. It's always going to remain the same, and of course the density will as well, because after all it's just the same string. Okay, now when it is in tune, we'll have a frequency F2 of 440 hertz. This is then going to correspond to a slightly different tension here in terms of the expression. Let's just call that T2. And then, like I did in the previous example, we basically just take one equation and divide it by the other. When I do, I'll come up with an expression for the tension T2 in terms of T1. If I then write the answer like that, then we can answer the question as it's phrased in terms of a percentage. Okay, so let's see. I'm going to be solving here for T2 eventually in this problem. So what I'll do here is I'll take F2 and then divide that by F1. So I have my F2 equation first in terms of tension T2. So, and then in the denominator of the expression, the frequency equation with my tension T1. So, and then like in the last example, a bunch of stuff cancels out. Two L's drop out, and as do the square root of the mu's, like so. But then if you just kind of clean up what is left over a little bit here on the right-hand side of the expression, we'll now have the square root of T2 divided by T1, like so. And then in order to solve for the tension here, T2, in terms of T1, we just square both sides of the expression and move the T1 to the other side. So completing that process, the tension T2 will just be F2 over F1, quantity squared, however, multiplied by T1. Okay, now my expression here for this ratio of frequencies, notice that it's going to be a number that's greater than 1. We're going to take 440 divided by 435 here and then square it. This then ultimately means that the tension T2 is going to be greater than T1 by a little bit. As we'll see, however, it's not all that much. So 440 over 435, square that, we end up with 1.02 times T1. So notice that it's just a very minute change in tension. In terms of a percentage, how much are we increasing the tension by in this problem? Now 0.2 or 0.02 is just 2%. So it's a 2% increase in tension. So this is why as you play the instrument over and over and over, as you do, you start to twist the pegs a little bit. That changes the tension a little bit. So you have to periodically pause and retune it. Changes in temperature will also cause the pegs to twist a little bit and so on. That's basically what's occurring when you're tuning a string instrument. Okay, one last example that's pretty similar to some of the web sign problems. That's why I'm treating it here. It has to do with some of the higher harmonics. As you can see, stringed instruments are pretty simple and straightforward. This, by the way, is my self-defense weapon. Not only do I use point with various stuff, the reason why it's here is because it's in the bag, just in case. Seriously, that's why I keep this handy. Never know.
If a student comes up and attacks you?
It hasn't happened yet, but it's not out of the question. I'm sorry. Okay, we kind of approach this the same way as the other example. We write down the frequency equation for two frequencies that are given. Initially, however, this is a little tricky. Now we have two successive, and these are right in order, harmonic frequencies. We have an F1, 360 hertz, and an F2 of 420 hertz. And then what we're solving for here is the fundamental frequency. Now remember how the harmonic frequencies work for standing waves on strings from, say, chapter 15. The harmonic frequencies are multiples, n, of the fundamental, which is the quantity from earlier, V over 2L. So what we're solving for here, specifically in this problem, is V over 2L. That's our fundamental frequency. Okay, now, how do I go about doing this? Well, we don't know which harmonics these guys are of the fundamental frequency, but we do know that they're successive. So then, therefore, if this frequency F1 is 360 hertz, it's some value of n multiplied by what we're looking for, V over 2L. So I'm just going to write it like that. But when I do, with this one equation, notice that I have two unknowns here. The two unknowns are the n, which I really don't care so much about the problem, and the other unknown is what's left over, and that's V over 2L, and that's what I'm trying to solve for. So this equation by itself is not enough. It's basically one equation and two unknowns. I need to come up with another expression. That's obviously where this next harmonic frequency comes in. Now we don't know what its value of n is either, but we do know that it's one more than this, because they're successive. So then therefore I'm going to write this harmonic frequency as quantity n plus 1 times V over 2L. If I now write the problem like this, I basically end up now with two equations and two unknowns. The two unknowns are n, which we really don't care about, and V over 2L. The easiest way to do the algebra in this problem, and this is why I'm showing this example, is to actually take the two frequencies and subtract them from each other like so. Because watch what happens when I do this. So I'm going to first of all take the F2, which is this guy here, and then subtract from that the F1, which was this one from up here, like so. And now if you approach the math in this way, notice what happens. Here in the first term, I'm going to get n times V over 2L, but then I'm subtracting from that also nV over 2L, which drops out completely. And all that I'm left with then is 1 times V over 2L, and that's what we're looking for. That is the fundamental frequency. And so then therefore the answer, which probably some of you already probably guessed, is just going to be 420 minus 360, which is 60 hertz. Notice that both 360 and 420 hertz are just multiples of 60. 60 times 6 is this guy here, 60 times 7 is this guy here. But that's the easiest way to show a problem such as this. Pretty simple and straightforward. Other than that, there's really not much else to just the strings themselves. That's how we produce the notes and so on a string instrument. But as you have now heard a couple of times with my guitar, it's not a very good guitar. One of the reasons why it's not a very good guitar is because the sound that it produces is not very loud, like so. So how do we amplify the sound acoustically? Not amplifying the sound electronically, that's kind of like a whole other ball game, but how do you amplify the sound acoustically? So next we take a look at what's called acoustical, using sound in other words, amplification. Without resorting to electronic amplification, there are basically two ways to do this. The first way to do this is very simply to just increase the size of the instrument itself. So in other words, if you just physically make the instrument a little bit bigger than it was before, then you just simply have more surface area to work with. The bigger the surface area associated with the instrument, the bigger the sound wave that's ultimately going to be produced by it. Oh, here it is. I've been looking for my tuning fork. Let me demonstrate in the following way. If I just strike the fork softly like so, it's obviously not very loud. So how am I going to amplify then the sound? Well, all I have to do is increase the surface area of the tuning fork by doing this. Because not only is the tuning fork vibrating, but the vibrating tuning fork causes the table to vibrate. And it vibrates at the exact same frequency. So then therefore the sound wave is not just being produced by the fork, but also by the vibrating table. Okay, listen to it again. Like so. So you can amplify the sound very easily like that. However, this is somewhat impractical because eventually your instrument is going to be so big that you can't carry it around, you can't play it. So there's a limit on the practicality of doing something like this. This is somewhat impractical after a certain point. There is instead, however, a much easier way to acoustically amplify the sound. And this is where you create what is called a sound box or a resonant chamber. The way that this works, like in an acoustical guitar, the chamber itself with the opening directly below the strings, the way that this works is as follows. You first of all set the instrument itself into vibration. And yes, it produces the Chladni patterns and blah, blah, blah that we saw on the body of the instrument last time in class. But in addition to that, the vibrating instrument sets up literally a standing wave of air, a standing sound wave inside the chamber, where an antinode associated with that standing wave of air appears at the opening of the instrument. This will then give you a nice, loud, clear tone, and an instrument that is well made will do this equally with every note that's played. So let me just describe this for you first of all here on the board qualitatively, and then I'll show you a number of examples of this. So second, perhaps instead, I guess I should say here, that is instead of just making the instrument really big, instead create a sound box, also what's sometimes called a resonant chamber. Because in this situation then, the vibrating instrument creates a standing wave of air, a standing sound wave inside the chamber. Sound wave inside the chamber. Antinode from this standing wave of air appears at the open end, as we say. Antinode. There's a standing wave of air. Appears at the open end. And then a well-made instrument will do this with every note that you play. Instrument will do this with every note. Now that sounds a little strange, but let me go ahead and demonstrate it for you. I'm going to demonstrate it for you a couple of different ways. First of all, the easiest way to do this is in the following manner. So using a graduated cylinder filled with some water, a tuning fork, and just a metal pipe, I'm going to create a sound box here for us. I'll do so by doing the following. Alright, so what I have here is a metal cylinder which I'm then going to just immerse into the water, like so. It will create what is called a closed pipe for us. You'll see what that means in a few minutes. Okay, then I'll take the tuning fork and strike it, like so, and then if I position the cylinder just right about there, I can now acoustically amplify the sound. Because what the vibrating tuning fork literally does is it sets up a standing wave of air here inside the chamber, and then by positioning it just right, I can get an antinode from that standing wave to appear here at the open end, resulting in a nice, loud, clear tone. So the vibrating tuning fork literally causes the air inside the chamber to resonate. The frequency of the standing wave of air, however, is exactly the same as the frequency of the tuning fork, because it's the tuning fork that sets the air here into vibration. In this case, it's at a frequency of 384 hertz. Let me show you a few more examples of this. Specifically, let me show you a couple of very primitive woodwind instruments. these whistles. These whistles, they're not very good. They're only capable of each playing 2 notes. In my first example here with this whistle, what I do is I blow into the whistle, and in doing so, I then set the instrument into vibration. And then the vibrating instrument, just inside of this rectangular box right here, and there's nothing in there, it sets up a standing wave of air here inside this box, such that you end up with an antinode here at this open end, and also an antinode at this open end. And this then sounds like the following. And by the way, when you listen to me do this, also watch the output over here on the oscilloscope screen. You're going to see that the waves are fairly close to each other. This then means that you get a high frequency sound. So it looks like this. Like so, and you can see that those waves are fairly close together. So by blowing into the instrument, you set it into vibration with a woodwind or a brass instrument. This then creates a standing wave of air inside the chamber. As we'll see with the math in a little while, however, you are constrained from playing a wide variety of notes in woodwind and brass instrument by the speed V. The speed V is always the same thing. It's the speed of sound, it's the speed of air, the speed of the air, the standing wave of air that is, inside of the chamber itself. You have no control over this. The only thing that you can control is essentially a couple of other things. You can, for example, first of all, play the open pipe, as I said, which looks and sounds like this. Or you can cap one of the ends. When you cap one of the ends, you create what is called a closed pipe. You still end up with an antinode appearing here at the open end, but here you've got a barrier. This barrier here literally prevents the air from vibrating at all. So instead of an antinode appearing here as it was earlier with the open pipe, instead you end up with a node appearing here at the barrier with a closed pipe. And then the frequency that results is exactly half as much as the open pipe. So once again, here's the open pipe first, and look at the waveform. So the waves are pretty close together. But now listen and watch what happens when I cap this up. It's a lower pitched sound. And because the frequency is lower, the waves are further apart. It's a lower frequency sound. So that's one way in which you can change the note. Skilled players with woodwinds and brass instruments as well, by changing the shape of their lips or by changing the mouthpiece of the instrument, can play some of the higher harmonics. And then the other way to change the note that's being played in a woodwind or brass instrument is to simply change the length of the pipe itself. You do this by pressing the keys on a clarinet or a trumpet or something like that. Because when you do, you're basically opening and closing valves within the instrument itself, thereby changing the length of the pipe. I don't have the ability to do this on a single whistle, so I'm just going to switch whistles. So this here is my bass. So first of all, playing it here as an open pipe. Okay, listen and watch. So, and then capping it up to play it as a closed pipe. The frequency here will be half as much as what you just heard. This is the bass. It's as follows.
Where does one get one of those?
These were actually made. They were made by myself and the previous physics teacher who used to work here before I came along. He and I actually sat down one afternoon and made those. Okay, so what's happening here with these pipes, these open and closed pipes? What does the waveform itself look like inside the chamber? Well, very quickly, there are some rather simple mathematical patterns that get picked up here. As we'll see, however, visualizing the patterns is a little tricky. I'll do a demonstration in a little while. However, using this tube here at my desk, they'll allow us to actually see the wave patterns themselves. Okay, but before we do, let's just make sure we understand the patterns. Okay, first of all, we have what is called the open pipe. Now, the actual geometry of the pipe could be really simple, like these rectangular boxes for these whistles, or it could be really complicated, like in a French horn or something like that, where you see the tube is twisted all around with a complicated geometry. That right there, by the way, is the sound box. But when it comes to the geometry, we ignore the complications and just think of it very simply like this. So right here is an open pipe like so. This is basically this rectangular box with two open ends, and it has length L. Now it is a little bit difficult to visualize what's happening here with this standing wave of air that's set up inside this chamber. But basically what happens is that at either of the two open ends, longitudinally, the air molecules are vibrating in place like so with a very large amplitude. In other words, you end up with antinodes here at the open ends. Now, how do we picture this mathematically? The way we picture it mathematically is by drawing a standing sine curve or a cosine curve. In order for you, however, to have two antinodes appearing at each open end, then your sine or cosine curve has to look like this. Antinode, antinode, like so. And then mathematically, we visualize this portion of this sine or cosine curve as oscillating in place like so. So half a period later, it would then therefore mathematically looks like this. Once again, this is just a representation of what's really happening. What's really happening is that the air molecules are vibrating back and forth longitudinally like so. We visualize this as a standing wave, a cosine curve, or a sine curve that's doing something like this. Now, if you look carefully here, say from this position to this position, like so for the red wave that I've drawn here, how much of a wavelength is there? It's 1/2 wavelength. So here in the space L, we have 1/2 wavelength. Watch what happens for the next harmonic. I'm not going to change the length L here. Someone who's playing a woodwind or a brass instrument can play the next harmonic by changing the shape of the lips or changing their mouthpiece. And the next harmonic would look like this. Okay, once again, here's the same space L. We'll say that that's exactly the same. But I now still have to have antinodes appearing here at each open end. That will give me a waveform that would then have to look like this. Antinode, antinode, like so. And then we visualize this mathematically as this cosine curve. In this case, is just oscillating up and down like this. So half a period later, look like that. Notice that it's a smaller wavelength than what I've drawn here above, meaning that it's a higher frequency. But pretty obviously, how much of a wave have I drawn here in this space L? Yeah, it's a full wave from crest to crest, like so. So here in the space L, it's just 2/2 waves, like so. So notice that I'm picking up exactly the same pattern here for the open pipe as we did earlier for standing waves on strings back in chapter 15. Notice here in the space L that what we have to have are multiples of just half wavelengths. So right here is the n equals 1. That will be the fundamental frequency. Here's the n equals 2, which is the second harmonic frequency or the first overtone, and so on. This means that the harmonic frequencies of these standing waves of air inside the open pipe is described exactly the same way as the harmonic frequencies that appear on strings. There is one major difference, even though the equation looks the same. Here's what I mean. Okay, first of all, the frequencies themselves are speed over wavelength. And the wavelength is 2L over N. Like so. So if you clean this up a little bit, you end up with NV over 2L once again. Harmonic frequencies of these standing waves of air, exactly the same expression as it is for standing waves on strings. However, here's the major difference. It's the speed V. Speed V is the speed of this wave of air. It's the speed of sound. You have no control over that when you play an open pipe instrument. The only thing that you can control is N, L. V, however, stays the same. So the V in this expression is specifically the speed of sound. It's the speed of this wave of air. And it's equal, mathematically, to 343 meters per second. So. Okay, now because of the bell schedule today, by the way, we pretty much do have a normal period today. The period basically ends at 2:06. So let me actually go ahead and take a break right here before we start to finish up this description and get to a few more demonstrations.
You roller coaster?
I do a roller coaster.
Yeah.
Like, to go on roller coasters, yeah. You know,
Oh, I do. Oh, do you roller coaster? Nah. Just ask Nash if you roller coaster.
you know, we agree that we're going
I like
to
roller coasters.
Oh, no, you're not with me. I'll get some of it.
Actually, you didn't.
Going to be riding. I was freaking out without Let's choose the second round.
I've been on Goliath,
So you have been on too?
It was
XC's a
closed.
lot to handle.
It was closed when I was there.
So right at the beginning of if the music is playing, if they have all the effects. It's so Okay, can you work on your notebook? How did you do last class?
It was Thursday.
Oh, it was Thursday.
And I left 3 days.
Well, I was.
Shouldn't have done that. Should have gone on Thursday. And I would have avoided literally 7 hours of trying to get my car parked.
So basically, I did all the conversion sets.
Yeah, it took me 7 hours.
Oh yeah, I heard
No.
right. Was that what the Snapchat was about?
Yeah,
I literally no idea.
don't understand. I was crying in my car at 1 in the morning.
Oh, sorry, on Friday night.
No, no worries.
Wait, you should talk
What?
on Friday night?
I was still trying to find a break spot Saturday morning.
So what'd you do on Friday?
We literally left it in the middle of the campground. Just abandoned it.
Oh my
At 1 in the
god.
morning.
I was gonna do all
I was so tired. I just wanted to be in my
Did
bed.
you guys hotel?
Really?
No, we were in an RV on site. Just like, because it was so full, because it was like, we had so much production and stuff like this year, they like didn't have room for extra cars. And so they're like, sorry, you person else. But then they would do working on us. And I was just like sitting in my car crying to my mom, and I was like, I don't want to sleep in my car. I don't know. Like, blankets, it was terrible. It was freezing. And I was like sweaty and dirty.
So,
Yeah, and we missed the Alalas, which is the Alalas.
oh, on Friday? Oh my god.
Yeah, and freaking, I was so excited to see Flynn in Wet'suwet'en, and then he didn't even come.
What's so
Yeah, he didn't even come. He wasn't even there. He was my number one. That was my number one. I mean, not like number, but like number one YouTuber. Yeah.
Who was your number one on the show?
I really like Chet Baker.
Oh, he's good.
He did a freaking good job. And like Tina Paul was great.
Oh,
Max
awesome.
Marco was so good.
You know, I haven't tried Marco. He was so good.
He's really honestly like okay, so I know a lot of people listen to him and I don't love him. So but I like his music a lot. So I was like, and I've heard like crowd surfs. I don't know, like I've heard like weird things about his performances. So I was like, and I've heard that he was like usually drunk and stuff. So I was like expecting him to be like falling all over himself and like kind of like not being be able to like understand anything that he was saying. And he ended up being one of my favorite performances. He was really good. And he was like funny too. And then
How long are
Stromae.
each of the shows?
Depends. Less important artists are like half an hour, 40 minutes. And then more important, like the headliners, like you don't have to stop.
Jack White. Do you see Jack White?
But like, the fact
I
that you can do it.
don't. We missed AC/DC, which I don't care either. And then Drake, I was gonna see him, but like, like the headliners were pretty shitty.
ACDC's No, I think Jack White's genius.
Honestly, so I was talking to my friend, Sandy, about this, and I think he's such a
Yeah, he comes in babies. He won the entire. But I don't.
him and the Black Keys,
Yeah.
like have like a feud going.
Black Keys.
Yeah, because he's like, they stole my art, like they stole my genre.
They're not gonna
Yeah,
accept
he
my.
it got to the point where he pulled his kid out of school because he was in the same school with the Black Keys.
Are you serious?
Yeah, and then he's like, and then like in an interview he said, yeah, sometimes I turn on the radio and I'm like, hey, maybe that's my song, and then I realized it's the shitty Black Keys.
No, Mr. Jack.
Yeah, so like he's just like pretentious to a whole nother level. Yeah. But I agree with him.
Yeah, but my roommate in college was an architecture major. He then ended up going to jail for 10 years.
Shit, something about it's like. a guitar documentary
Story, don't major.
called something. It's not loud. Or, I don't know. Anyway, he's in it. Jimmy Page is in it.
Yeah.
It's like,
Oh,
Jimmy
it's the Edge.
Page, the Edge,
Is he no, who's maybe it was no, it wasn't.
That's.
It was either Jimmy Page or Keith Richards. I forget which one it was.
I want to say, I know that John Bonham's dead. Is Jimmy Page still alive?
Yeah.
Yes, Jimmy Page is still
I'm
alive.
sorry. There he is.
He's about 70.
All right.
Okay,
He's still
there you
alive.
go. Wasn't
He's
sure
aging
how many
well.
of them
Our
died
Plant Arbor's not.
Oh yeah. Have you
Our
seen?
plant doesn't look that good.
off.
Have you seen? Yeah, at least he's still doing music. But
Yeah.
did you see? There's a documentary with U2's The Edge, Jack White, and either Jimmy Page. Have you heard of it?
No, not specifically. I mean, I like Zeppelin, but I don't really like them.
Okay.
Not my thing.
Yeah.
Have you seen Dave Grohl's Sound City and that whole?
I haven't know. I think I've seen one of them.
Okay, I really recommend his documentary. I recommend the documentary Sound City, and then I recommend watching. Don't watch the album. Watch his TV series.
Did you see Seattle one?
Yeah.
Has Ben Gibbard in that?
I haven't been that long. See, not the
He's
biggest.
from Seattle.
I'm not the biggest DC
I like my favorite.
Really? I'm sorry.
Oh no, it's okay.
All right, let me go ahead and move on.
You're more of a.
Move on.
Oh, I guess Chet Baker's not.
So then, secondly, we get to the closed pipe, which, as you'll see, is definitely a little bit trickier to visualize and also describe mathematically than the open pipe. Okay, Lena, Henry, here we go. Okay, now, first of all, just kind of generically, we draw the closed pipe geometry like this. Just as, once again, a rectangular box here of length L, but now we basically have a wall over here at one end. One end is capped. Now, basically what the wall prevents the air from doing is it prevents it from vibrating back and forth. So then, therefore, what you have to have right up against the wall is a node, whereas over here at the open end, you still have an antinode like so. Once again, this is all occurring with a sound wave, so it's longitudinal. So the antinode is basically doing this, whereas here at my left hand, you have a node. Now, for the fundamental frequency here, the situation then therefore, in terms of the waveform, looks a little weird. We have to visualize it like this. Node, antinode. And so then therefore, you end up with just this piece here, this portion of a sine curve, for example, which then we picture mathematically as oscillating like this. So a half a period later, it would then oscillate here. Now, if you do look here carefully, how much of a wavelength, what fraction that is here in this space L?
A quarter.
Yeah, it's a quarter. Like so. But watch what happens for the next harmonic. I'm going to once again keep the L here the same, but it's like I changed the shape of my lips and then therefore play the next harmonic. So in the space L then, the next harmonic will have to look like this. We'll still have to have a node appear here at the closed end, and then an antinode at the open end. So then therefore the waveform will have to look like this. Node, antinode, like so. Once again, longitudinally, the air is just doing this, but now mathematically I have to visualize it as a portion here of the sine or cosine curve oscillating up and down, such that half a period later, it looks like that. Now, yeah, admittedly that's a little bit weird looking, but if you look carefully there in the space L, how much of a wavelength is there? Yeah, it's 3/4. So L here is equal to 3/4 lambda, like so. So you don't end up with multiples of quarter wavelengths, you end up with odd multiples of quarter wavelength. So we have to use an odd multiplier to describe this, much like we did, for example, when talking about two-source interference at the end of chapter 15. So in the space L, we have to have odd multiples, 2n plus 1 of lambda over 4. The terminology for the closed pipe gets a little bit confusing, however, because of how this odd multiplier works. This right over here is n equals 0, because then in parentheses you'll end up with just lambda over 4. But when n is equal to 0, that's the first harmonic frequency. That's the fundamental frequency. And then when n is equal to 1, That's actually this situation here, where the space L is 3/4 lambda. This is then therefore the second harmonic frequency, called the first overtone, and so on. Don't get bogged down, by the way, in the jargon and the terminology, especially with closed pipes, because it is a little bit confusing because of the odd multiplier, but just know the math behind it, which is fairly straightforward. We just have odd multiples of quarter wavelengths appearing here within the closed pipe. Same sort of expression, however, for the harmonic frequencies as well. Frequency is speed over wavelength. Okay, the wavelength is 4L divided by the odd multiplier. That looks like this. And then if you clean up the expression there a little bit by putting the odd multiplier into the numerator of the expression, you then end up with the harmonic frequencies as being odd multiples of the quantity V over 4L. So the fundamental frequency associated with the closed pipe is the quantity V over 4L. For the open pipe, still up here on the top board, it was V over 2L. So that's basically what you were hearing with each whistle. With each whistle, first of all, as an open pipe, this right here is the V over 2L, like so from the top board. And then when I cap it like this right here is the V over 4L, which is exactly 1/2 as much, like so. And then if I make the L bigger, either here for the closed, or here for the open by switching to my other whistle, if I make the L bigger, then therefore the frequency goes down. Now it's easy enough to see these patterns here as they appear on the board, but actually visualizing the standing wave of air itself inside the chamber is a little bit tricky to do. So let's go ahead and actually see the standing waves. So how do I go about doing this? Well, I'm about to show you a very famous physics demonstration that was dreamt up by a high school physics teacher back in the 19th century. This is referred to as a Rubens tube. The way that a Rubens tube works is it's kind of like a really big Bunsen burner. So what I have here attached to my gas jets is the tube itself. And then when I pump gas into the tube, those of you that are close will see that there's a bunch of holes here at the top. What I will then do, kind of like with a Bunsen burner, is then light the whole thing. I'll have a flame that is coming out of each individual hole. And then right over here off to the side is a little rubber membrane, like so. And what I'm going to do is take a speaker, this is one of my Bluetooth speakers from home, just place it right up against the rubber membrane like so, and then I have my phone Bluetooth to the speaker. You can download a free function generator app on your phone if you're so inclined. And then what I'm going to do is then send pure tones, function generator tones, through the pipe itself. The way this will then show up, how we can actually see the standing waveform, is that antinodes will appear where the flame is large. The reason for that is because you're seeing a high pressure. So in other words, the air molecules are moving very back and forth with a big amplitude. That's a big high pressure. The nodes will show up as portions of the wave where the flame is small, because that will then correspond to very little movement associated with the air molecules. Those will correspond to nodes then with relatively low pressure. That's the basic idea as to how it works. So let me go ahead and start to throw some gas into this thing. So, and then I just light it up. Blast it, increase the pressure a little bit, like so. Yes, you'll turn it down a little bit. Turn it down a little bit. Like so. And now with the function generator app here on my phone, I downloaded the free one, so I have to look at the commercial first. Yeah. Okay, so now you're going to be hearing 336 hertz when they turn this thing on. Oh, like so. And you can see pretty well delineated right here is an antinode. And kind of off to the side, maybe here, a little bit over here, is the beginnings of a node. Now watch what happens as I change the frequency around. That's a little too low. wavelength that you're seeing, because it's basically like node, crest, and then node again. So what I basically have to do is I have to adjust the frequency here on the function generator such that speed over frequency equals wavelength. The wavelength, is about the size of the tube, or a little bit greater or a little bit less, such that we can actually see the waveform itself. In other words, if I make the frequency too small, then the wavelength is going to be too big, and you're not going to be able to see it over this distance. If I make the frequency too high, just pause it. If I make the frequency too high, then basically the wavelength is going to be too small, and you won't be able to see it. So you have to play around with the frequency here in order to see a clearly delineated sine or cosine curve. Let's try it again. Well, that's pretty good. Right there. That's probably about a full wavelength. So it's like crest. Well, actually, it's a full wavelength. Crest, node, trough, node, crest, like so. So right there is basically a full cosine curve like so. That's about as perfect as I can get it for those of you that are taking pictures. Okay, I actually get a picture of this right now. I'll Instagram it later. That's pretty good, like so. Okay, then if I... Oh, you want to take the flash off, guys? That's okay. All right, now I'll change the frequency around a little bit. Now it's starting to get to be too high a frequency such that the wavelength now is pretty small and we really can't see it here within the flame. Right about there is probably the best one. That's pretty good too. So once again, here's about a half wavelength, like from crest to node to trough, like so. Remember that the antinodes are crests and troughs. Okay, right here is maybe about a quarter wavelength. So maybe like crest to trough, like so.
It's the shooter.
See, he missed it. See, he missed it.
It's like...
Now, does this, of course, work with music?
Yes.
Absolutely.
Oh,
Let's try that. Let's try music. Now with music, it more or less just kind of bounces around a little bit. It really doesn't do all that much.
What's your favorite song?
Well, remember my second job is being a music critic, so. Let's try this. Here, let's crush your skulls a little bit. See, with music, it just kind of bounces around a bit, and that's about it. Yeah, so with music, it just kind of bounces around a bit. You need to really be able to see it with nice, clear tones. Now, how many of you took a look at that YouTube that I posted last week on Chladni patterns? Well, I put up one there this morning. Some graduate students in Europe somewhere built a two-dimensional Rubik's Cube. It's called a pyro board. So I encourage you to take a look at that. Okay. All right, let's take a look at a couple of problems associated with open and closed pipes. They're all pretty simple and straightforward, much like the problems we saw earlier associated with the release on a string. Okay, when it comes to the open and closed pipes, however, let's take a look at first in detail the opening demonstration that I introduced you to this concept of the resonant chamber. That is, let's take a look at this demo here once again in detail. It's a little bit tricky to visualize exactly what is happening here in this demonstration. Okay, now the numbers here in this problem are exactly how I've set up the demo. I do have a frequency here for my tuning fork of 384 hertz. Okay, now the math behind this problem is pretty simple and straightforward, but visualizing what's happening here is definitely a little tricky. Okay, so here's basically now in detail how this demo works. So we start off, first of all, with our graduated cylinder like so, filled with water, and then right here is the water line. And then what I do is I immerse the metal cylinder into the graduated cylinder of water, like so. And then the way that this behaves is as if it's a closed pipe, where the water line is the wall, the open end is right here at the top. And then what we do is we take our tuning fork like so, set it into vibration. The frequency of the fork is a given, is 384 hertz. Now it's critical to understand that the frequency of the standing wave of air inside the chamber is exactly equal to the frequency of the tuning fork, because it's the tuning fork that creates a sound wave here. So the frequency of the tuning fork is the same. As that of the sound wave. Okay, now we're positioning the tube such that what we're trying to find here is the length of our pipe L, such that we hear the N equals 0 antinode appearing at the open end of the pipe. Now from our odd multiplier equation for the harmonic frequencies of a closed pipe, the equation itself then therefore is as follows when N is equal to 0. It's just V over 4L. Now the frequency of the fork here is given as 384 hertz. The speed of sound V also is a given for this problem, is 343 meters per second. Once again, this is specifically the speed of the sound wave inside the chamber. So then therefore mathematically all that I have to do here is calculate what L is in terms of meters and then demonstrate it as to exactly what's happening. So mathematically there's not much to this problem once you visualize what's occurring here. So then therefore I'm just going to solve for L by cross multiplying. The length L here is then V over 4 times F. So now calculating that out, it's going to give us here a distance in terms of meters, and then we'll test it here in the actual demonstration itself. So I have 343 and then divided by 4 times 384, and that gives me then 0.22 meters. This is 22 centimeters long. Okay, now on this particular cylinder, I've taped here a ruler like so, where 22 centimeters is about this distance here between my fingers. So that's about how big I have to make the resonant chamber, such that we can hear the resonance with the tuning fork itself. So that then looks like this. And yeah, sure enough, right about there is 22 centimeters like so. Now the way that this will eventually work after we get back from Magic Mountain is with a laboratory exercise. Because with our laboratory exercise, we're going to use this setup here to measure the speed of sound. And it's actually really easy to do. Basically what we are going to do with this equation here is for various tuning forks of frequency F, which we know, we're going to measure L such that we hear the N equals 0 antinode. And then therefore if you're measuring L and the frequency F is a given, what's the only unknown? V, the speed of sound. So using this expression to measure the speed of sound is actually really easy to do. Yes?
So they're like a little engraving on the fork?
Yeah, it's stamped on the side, much like the slotted weights that we use for various experiments. Yeah, they're stamped on the side. So the frequencies will be givens, and then after that we just measure L, and then from there we can figure out what the speed V is equal to. Now the actual waveform that is appearing here inside the pipe, it's a little tricky to visualize because it's just kind of tipped on its side from what I drew earlier. Let me use a different color to describe this. We have the water line, which remember is our closed end. And then the open end is up here, of course, at the opening at the top here of the tube. Such that you have a node here and an antinode here, and when we're hearing the N equals 0 antinode, we have to have a quarter wavelength and therefore fitting inside the tube. So that kind of looks like this if you draw it from the side. Like so. So here in brown is my quarter wavelength. So we have an antinode here and a node here. Now as I was moving the tube up and down just right until we could hear it just right, if I'm off of it a little bit, if I'm off of the antinode, you're still hearing the same sound. It's still the same wave. It's just that if I had the open end position right here, you're just hearing a softer sound, a smaller amplitude than you would right here where an antinode appears at the open end. So that's what's occurring in detail in this problem. Okay? Okay, a couple of other basic examples to take a look at. This is also, once again, a fairly easy topic. Let's take a look at one involving harmonic frequencies, similar to what we saw earlier with standing waves on a guitar string, for example. But when it comes to the closed pipe, the math of the equation, because of the ohm multiplier, is a little trickier to work with. So I want to take a look at one specific example that illustrates that. We'll take a look at this. Okay, so we have an organ pipe. The organ pipe is obviously a nice example of a resonant chamber. The organ pipe resonates at the following 3 frequencies, but nothing in between those. What we have to figure out, first of all, is whether or not the pipe is open or closed, and then after that, what the fundamental frequency is equal to. This problem is definitely a little bit trickier than the, that's a new word for you. It's a little trickier than the earlier example involving the waves on a string, the harmonic frequencies on a string. All right, so here's what we're given. F1, 264 hertz. It's definitely getting closer and closer to the end of the year as I trip over my words. F2 is 440. And F3, call it is 616. Okay, now let's make the following assumption first. Let's assume that it's an open pipe. So if I make that assumption, then the harmonic frequencies are the multiples of V over 2L. And I'll initially approach the problem then much like I did with the string problem from earlier today with the successive harmonic frequencies. I'm just going to take a look at the first 2. The third here is really not necessary. I'm going to write an expression for F1 in terms of N, and then we have the next harmonic up, N plus 1. So the F1 is going to be NV over 2L, and then the F2 will be an N plus 1 times V over 2L. And then like I did in that earlier example, I'll just subtract one from the other and let's begin to see what happens. So now mathematically, we'll take F2 minus F1, which is then this guy here, minus this. And then remember here how the math works. We're going to have an NV over 2L minus NV over 2L, which drops out. And then all that's going to be left is 1 times V over 2L, which is just V over 2L. Now numerically here from the left-hand side, it's 440 hertz minus 264 hertz, which is actually 176 hertz. So in other words, if this organ pipe is an open pipe, then the fundamental frequency is 176 hertz, and these guys here then therefore have to be multiples of that. So let's see if it works. Well, if I take 176 hertz, multiply that by 2, I end up at 352 hertz. It's in between these two guys here. That doesn't work. If I take 176 hertz and multiply that by 3, that's 528 hertz. That's in here, it's in between these two values. Once again, that doesn't work. So therefore, it can't be an open pipe for this reason. It's not an open pipe. So then therefore, it has to be a closed pipe. However, with the math associated with the odd multiples of the closed pipe, this is where it gets a little tricky. Because the harmonic frequencies of the closed pipe, remember, are the odd multiples of the fundamental, which is V over 4L. Now what I'll do here with this expression is much like I did up on the top board. I'm going to write it for F1, write it for F2, and then subtract the two from each other. When I go from F1 to F2, however, I do have to increase the value of n plus n here by 1. When I do this process, though, you got to be really careful in doing so. Here's what I mean. Okay, first of all, the F1, we'll just think of like this. And now the F2, we're going to make the n plus 1. Therefore, I have to think of it like this. I'm going to use brackets here to illustrate. It has to look like this here. So notice what I did there in brackets. I took the value of n and I increased it to n plus 1. Now if you multiply the brackets here out, notice that you're actually going to get 2n plus 3. Because you'll have here 2n and then 2 plus 1 here like so, for a total of 3. You're going to end up with this. And then like I did in the last example, I just subtract one from the other. Watch what happens, however, as I do this. So now I take F2 minus F1. So we have the 2n plus 3 times V over 4L minus 2n plus 1 times V over 4L. And then here's the math. Okay, first of all, I'm going to have 2n times V over 4L minus 2n times V over 4L. That drops. Then I'm going to be left with 3 times V over 4L minus 1 times V over 4L, which is 2V over 4L. Notice what happens, however, if you cancel out a 2 from the numerator and the denominator. When you cancel out a 2, you end up with V over 2L once again. And then numerically, it's the same thing as it was before. It's 440 hertz minus 264 hertz. It's equal to 176 hertz. So it looks like I just talked myself into a corner again, because I end up with what I had up here on the top board for an open pipe. But we know already that it's not an open pipe. So this doesn't work. So what do I then have to do? Well, what I do is I take this here and I divide the 2 here to the left-hand side. Because when I do, what I'm solving for is V over 4L, which is the fundamental frequency of the closed pipe. So if I now take 176 divided by 2 to give me V over 4L, 176 over 2 is 88 hertz. So according to what I've just calculated, the fundamental frequency of the closed pipe is 88 hertz. Then these 3 guys that are given here, they have to be odd multiples of that. So let's see if that works. For example, if I take 88 hertz and multiply that by 3, I get 264 hertz. If I take 88 hertz and multiply that by 5, I get 440. If I take 88 hertz and multiply it by 7, I get 616. So then therefore, yes, it's a closed pipe with a fundamental frequency as 88 hertz. So the problem I did earlier today involving the successive harmonics on a guitar string, that was easy. The closed pipe, however, with the odd multiplier is definitely a little bit trickier. Here's a nice illustration of that. Okay, lastly, however, for open and closed pipes, this is obviously a pretty simple and straightforward topic. One last thing is a little bit of our physiology. Open and closed pipes, in terms of your own physiology, occurs 2 different ways. Okay, first of all, when you speak. When you speak, I'm obviously speaking to you here at a high volume when I do, but the amount of energy that I need here to speak is not all that much. So then what amplifies the sound of my voice? What amplifies the sound of my voice is my voice box, my Adam's apple, my larynx. My larynx is an example of an open pipe. Because as you speak while you exhale, basically what you create is a standing wave of air inside your larynx, such that you end up with an antinode at your opening, which is basically where your mouth is. So this will then result in a nice, loud, clear tone as you speak. Do a little bit of an experiment for yourself. Go ahead and place your hand on your Adam's apple, and then go, like so. And then, yes, you can go ahead and you can feel it vibrating. So your larynx is an example of a sound box. That's why it's also sometimes called your voice box, for this reason. But then also, in terms of your hearing, your ear actually acts as a closed pipe. The reason why it acts as a closed pipe is because, yes, it's open at one end at your opening, but down below, you have your eardrum, which basically caps the other end. So your ear is a closed pipe. Specific frequencies will resonate within your ear. They are very high-pitched frequencies, however, and this is one of the reasons why we find very high-pitched noises very annoying. Remember that little test that I did about a week ago where I raised the frequency and we tested everybody's hearing? As soon as I got above a couple of thousand hertz, everybody started going like that. Everybody started wincing a little bit. Those frequencies are sometimes described as piercing. And the reason why is because at 3 values of them, specifically you end up with a resonance that occurs inside your ear, and the tone is actually quite loud and very annoying for this reason. Let's take a look at that as a final problem associated with closed pipe. Analysis here. Sorry, you need to answer something. Okay, now the human ear canal is about 2.5 centimeters long. So the L here in this problem is 0.025 meters. And as I said, the human ear basically acts as a closed pipe. So then therefore the resonant frequencies will be described by the following odd multiplier equation, where once again the speed V here is the speed of sound at 343 meters per second. So what I'm going to do here is just calculate out a couple of these frequencies that are particularly piercing, as we say. As you'll see, they're all really high pitched. This is basically where you end up with a standing wave of air inside your ear canal. Now I only need to calculate a couple of these because as you'll see they're all pretty large frequencies, they're all really high pitched, and eventually you get to a point where you can't hear them any longer because you're above the audible range of human hearing. You get very quickly to a value above 20,000 hertz. So let's go ahead and see what happens first of all for n equals 0. For n equals 0, then the frequency is just going to be V over 4L, but the L here is obviously pretty small. This then means that the frequency itself is going to be pretty large. 343 divided by 4 times 0.025, which is mathematically equal to 3430 hertz. So this is already really high pitched, this first resonant frequency. This is really why we find very high pitched sounds annoying, and in some cases almost painful, because in particular, this one here is going to sound really loud. Now let's calculate out what happens when n equals 1. When n equals 1, the frequency is just 3 times as much. So multiply that by 3, and this is even bigger still. This is 10,290 hertz. And then I'm just going to do here one more when n is equal to 2. When n is equal to 2, this becomes 5 times the original value of 3430. 5 times 3430 works out to be about 17,150. Like so, I'm not going to bother calculating past that point, because when you do, you get above the audible range of good hearing. So we hear these sounds as particularly loud and stuff that's close to it as well. That's why really high pitched sounds are particularly loud. All right, good enough for that. No, not finished yet. Almost. 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 Let me just introduce you to our next topic before we do the next topic today in a few minutes. But I do want to give you a short introduction to it. Okay, our next topic here is specifically on what is called Doppler effect. Now, this is not going to be for light or radar, which, by the way, is exactly the same thing. Instead, this is the Doppler effect of sound. There are two physically distinct types of Doppler effects. The first occurs when you have a moving source of sound. Okay, let me demonstrate this force for you first and why it works the way it does. So for example, let's just for context here, say that you're standing on the side of a road and the siren is coming towards you and then the siren passes you. So you hear that very particular high-pitched sound, and then all of a sudden the pitch changes and it's low-pitched as it goes by. It's kind of like that type of sound that you hear when a siren moves past you. The reason for that is as follows. What I'm going to do is physically demonstrate it for you here by means of this tuning fork. I'm going to give the tuning fork a whack, and then I'm going to twirl it above my head. When I do, when the tuning fork is moving towards you, the sound waves that it emits towards you, their wavelength is going to be physically compressed a little bit, as opposed to if the fork was stationary. If the wavelength is smaller than it would be if the fork was stationary, and the speed of the sound wave is the same, this then means that the frequency is going to be larger. You're going to hear a higher pitched sound for that reason. If, however, the tuning fork is moving away from you, the sound waves that it emits towards you are kind of stretched out a little bit. They have a slightly bigger wavelength than they would if the fork was stationary. So then therefore, if the wavelength is a little bit bigger, then therefore the frequency is going to be a little bit smaller. So you're going to hear a low-pitched sound. So this is the first type of Doppler effect where what we're physically changing here is the wavelength of the sound wave itself. And it basically sounds like this. Like so. So when the fork is moving towards you, the wavelength is compressed a little bit, resulting in a higher pitched sound, a higher frequency. Fork moving away results in a stretched out wavelength, a lower pitched sound. Okay, visualizing this with this little applet that I have here is actually fairly simple and straightforward. It basically looks like this. What we have right here is a source that in this case is going to be moving at half the speed of sound. And as this source moves, it's basically going to beep. It's going to go beep, 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 and so on. And watch what happens when I set it into motion, like so. Notice that in front of the object, the wavelength is compressed a little bit. So then therefore, if you were an observer standing right here and that source is moving towards you, these waves, when they reach your location, have a smaller wavelength, but the speed of the sound wave is the same. Speed equals wavelength times frequency. So if you make the wavelength smaller, the frequency then therefore has to be larger. So you hear a higher pitched sound for that reason. And then if the siren passes you, and you're standing, say, over here, notice that the wavelength is stretched out a little bit. If the wavelength is stretched out a little bit, then this then means that because the speed of sound is the same, the frequency is going to be smaller. So it's going to be a lower pitched sound. So this is the first type of Doppler effect that occurs if you have a moving source. Okay, now let me zip it back over to the middle of the diagram in the other direction. This is, by the way, what happens if you go faster than the speed of sound. We'll get to that a little bit later on. But now what I'm going to do is just move the source here into the middle of the diagram, and now I'm going to put it at rest. So now it's just sitting there going beep, 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 and so on. Okay, the second type of Doppler effect will occur if you have a moving observer. So let's say that we have that stationary source. You're standing over here, and you now start running into the waves like so. Notice that the wavelength doesn't change, however, in this situation. But what does change is the speed of the sound wave according to the observer. It's a little bit of Galilean relativity. So in other words, if you run towards the source, are you going to see the speed of sound as being equal to, greater than, or less than 343 meters per second? It's going to be a little bit greater. So then therefore, if the speed is now bigger than it was before, but the wavelength is the same, the frequency is then therefore going to be bigger. So you're going to hear a higher pitched sound in this situation, but it's for physically different reasons than the situation I described earlier with the moving source. So basically, if you run into the sound waves like so, you're going to see a bigger speed to the speed of sound, resulting in a higher pitched sound. If you run away from the source slowly like so, you're going to see the speed of sound as being less than 343 meters per second from Galilean relativity, and then therefore you're going to hear a lower pitched sound. So there's two physically distinct Doppler effects for this reason. In the first example with the moving source, it's a changed wavelength, therefore changing the frequency. In the second situation, however, it's a changed speed of sound according to the observer. So it's a little bit of Galilean relativity, as we'll see when we run through the math a little bit later on. This then results in a changed frequency. I guess I should change all of this. So, as we see, however, describing these physically distinct Doppler effects mathematically is actually pretty straightforward. Okay? All right, let's go ahead and take a look here at 4. What I've done with the board here with this week's website is I've kind of cut it off a little bit, simply because, of course, we have our interruption in the middle of this week for our Magic Mountain trip on Wednesday. So then, therefore, the only portion of the web assignment that's due next time is these 4 problems. That's basically the first half, but the other half I'm just holding off until next week. All of this stuff here is just on open and closed pipes, guitar strings, and so on, like we described here today in class. Pretty simple and straightforward, okay? Don't forget to bring the materials that you need, your protractor and so forth, for the field trip as well next time in class. Hopefully that you have that one person in your group that is assigned to keep track of it, and they bring it on Wednesday, and I'll see you at the flagpole on Wednesday at about 9:15 or so. Don't forget your little cardboard ticket there, your construction paper ticket, so you can get onto your bus.
What is the deal with that? What is already told you? What do we have to do?